and they take very different approaches to the bank software. Usually they have no sort of representation of the graph. So recently I've been thinking, can I do the bank sort of stuff without having a detailed representation of the graphical model? So I've been fiddling around to see how far I could get. So it's been sort of tearing the bug software into bits, reassembling them without having the graphical model. So a bit of background, you can describe the joint probability, the statistical model by a joint probability distribution. This is usually a very complex function of very high dimensional space. And you can represent that as a graph, usually a directed acyclic graph, but more generally a chain graph. The graph shows the factorization of the probability distribution function. So the Gibbs type algorithms use the factorization of the graph to make computation more efficient. So one of the things I've been pondering is how to get this factorization so that you can do Gibbs type algorithms if you don't explicitly build the graphical model. So the bug software does two types of computation on the graph. The second is fairly obvious. You want to calculate things like probability distributions or summary statistics so that you can exploit conjugacy. But you need some way of knowing what numerical computations you want to do. So for want of a better word, I'll call that meta computation. So you look at the graphical model and so try and extract structure from that graphical model and conjugacy relations, any sort of relations that will allow you to optimize the computation. So this has a knock-on effect. You need to build a representation of the graphical model that you can extract the information that you require from. Next slide, please. So in the bug software, each node in the graphical model is aware of what its parents are. So once you know the parent structure, you can find the children. That's a non-local computation. So you do it once for the graph, and then you cache the information. Once you know for each node in the graph who your children, who your parents are, you can calculate the Markov blanket. You have the Markov blanket. So you can do Gibbs type algorithms. They needn't be strictly Gibbs sampling. They could be component-wise, Metropolis Hastings or slice sampling, or maybe Langevin, that sort of algorithm. But it's quite a messy business manipulating the graph. So I'll be looking for alternatives. Okay, can I have the next slide? One of the things that more modern Markov chain Monte Carlo algorithms need is the derivatives of the joint probability distribution. In a way, you can get those derivatives by differentiating the conditional distribution. Maybe there's more efficient algorithms which does the differentiation all at once, but doing it one parameter at a time does work. Once you have the derivatives, you can do Hamiltonian, Monte Carlo, automatic differentiation, variational inference, Langevin algorithm, and various other things. So that has been put into the bug software and it works, but maybe rather slowly. For very big models, HMC can be a bit on the slow side. Can I have the next slide? Okay, so looking for an alternative to building detailed representation of the graphical model out of sort of mass of objects of dozens and dozens of classes. One alternative is to just derive some imperative code which allows you to calculate what you need. This is extremely easy if all you need to do is calculate the joint PDF. For HMC, ADVI, you also need the derivatives. So that can be done. Stan does it very well. So I've been playing around, first of all, how to write source code that will calculate the PDF, and then how to do the derivatives. Next slide, please. So it's quite different from the bug software. You don't have any explicit graph that you can wander around discovering interesting things. You don't have any Markov blanket. So how do you do Gibbs type algorithms? You could think this is all a very good thing because you don't have the graphical model, you don't have to build a graphical model, you don't have the graphical model occupying tens, maybe hundreds of megabytes of core memory in your computer. So it's good and it's bad, and I'm not sure what the balance of good and bad is at the moment. I've not got far enough. Okay. So to do Gibbs type algorithms, you need the conditional distributions. You can always calculate the values of the conditional distributions by calculating the joint probability distribution. It's just rather wasteful if you have a sparse model. So I've been playing with the idea of adding some control structure to the imperative code that I generate for the PDF, which allows you to only execute sort of part of the code for the PDF. If I can do that right, then I have a way of evaluating conditional distributions fairly efficiently. Can I have next slide, please? So I had sort of two ideas that came more or less at once. The first one is just to add a case statement to the code that calculates the joint PDF. So that would allow me to just evaluate certain statements. The second thing is generally in a probabilistic programming language, you have loops over, say, all the observations or over all of the data variables. When you're doing conditioning, you generally only want to evaluate certain elements of the loop. So, a very simple idea, just to specify the indexes of the elements of the loop that you want to evaluate. So you can just partially evaluate loops in the model. So that is what I've been trying to do, to sort of feed extra information into the compiled code for the PDF, which will allow it to calculate conditional distributions, and then I can build Gibbs sampling algorithms or other more complex algorithms on top of that. Can I believe next slide, please? So it's just a matter of giving some extra arguments to the PDF function. Those arguments are just an array of integers. So the first integer will correspond to the sort of line in the compiled code, or the line in the probabilistic model that you want to execute. And then after that, there'll be a whole bunch of integers which will tell you which statements in a loop statement, which elements of a loop you want to execute. There's an optimization fairly obvious. Sometimes you want to evaluate all of the loop, and in that case, just give it a single integer, the sort of line number in the PPL or the compiled code. So once you have these vectors or integers, they give you the conditional independent structure of the model. So all you need to do is have a way of calculating these integers, and then you can do a Gibbs sampling approach to any model. The next statements. You can use this idea also partially executing code to handle conjugacy and calculation of sufficient statistics. You just generate slightly different source code which you compile. You can use the same idea to write the classification code which allows the BPL to choose which sampling algorithms to use. There's a few caveats to this approach. You need to impose some order on the statements in the PPL. In a way, this is quite similar to what Stan requires. Slightly laxer in the way I process the PPL. It's easy to separate into deterministic logical statements and stochastic statements. That's statements which either have a sort of left pointing arrow for deterministic statements or a tilde for stochastic relations. It's very easy to separate the PPL into the statements of the PPL into those two classes. It's necessary to order the logical statements in sort of use order or depth order, nesting order. The Bug software could do that automatically, so I'm hopeful I can do away with that requirement later on. Okay, next, please. So how would you find these integer arrays that allow you to do the conditioning? And it's a very simple algorithm. You're sort of doing an abstract interpretation of the imperative code that you generated. Instead of dealing with real quantities, you deal with Boolean quantities. It's for small models, it's really, really fast. You don't notice it. For bigger models, it's a little bit slow. So I need to work on that. If, so when I talk about big models, I'm talking about a few 100,000 observations, a few tens of thousands of parameters, not huge in machine learning in terms of, or statistical models quite big. So it's the algorithm I have for finding the conditional structure isn't terribly efficient, but it's embarrassingly parallel. So for big models, you'd be running on multiple cores. So I'm not that upset that the algorithm doesn't run lightning fast, because I can distribute it over 10 or 20 cores, and then it will be pretty fast. Okay, next slide, please. So I have some early results. What I'm aiming for is to sort of reproduce the functionality of the bug software using the new representation and new computational representation. Not everything is running. There's about a dozen models running. I've had to re-implement the sampling algorithms and re-implement the sort of distribution algorithms, the algorithms that represent things like normal distributions or binomial distributions, but generally that's been sort of cannibalizing the bug software, ripping bits out of that. For an example of the sort of performance of the new approach, I go back to the RATS model, the first model the bug software ever ran, and it's a small model, 65 parameters, 150 observations, and in the new software, it runs about 25% faster than the bug software, which I think is quite encouraging because it's a particularly simple model. So the bug software is already quite efficient for that. 100K samples from the model takes 2 seconds compared with 2.5 seconds in the bug software. So that's pretty quick. Can I have the next slide? Oh, I messed up on that one. Okay, so for a more realistic size model, I compare the approach in OpenBugs with the new one. I get much smaller memory footprints, 50 megabytes instead of about 176. So that's a big gain. That should allow me to do, say, a model 10 times as big. The compensation would aim to compile the model, so that's generating the source code, compiling the source code, and then calculating conditional structure, choosing all the update algorithms is a bit worse. For the new approach, it's 115 seconds compared with 62, but all the time is in calculating a conditional structure. So if I parallelize that, I think I will beat the time it takes OpenBugs to do them, compile the model. Okay, runtime is hiding at the bottom of the screen. I'm getting very comparable runtimes. So it's looking encouraging. It's very early software. I've only been working on it for a month, 6 weeks, so I'm sure it will improve. Okay, can I have the next slide? I've made heavy use of the bug software, the parsing, the abstract syntax tree, a few other data structures have come over completely unchanged on the bug software. When I generate the source code, I do it in component Pascal language because it's a language I program in. It's a language that bugs has been coded in. It's the only language I understand now. But it should be possible to translate the PPL into another language. Julia is looking very attractive objective to translate into, but could certainly translate into C. The source code that gets produced from the bugs PPL is very easily readable and it's well structured, but it tends to be a bit repetitive for those, but certainly you can find your way around, reason about it and debug the software when it's not doing what you hoped. Next slide. Current work, I'm trying to add a type system to the bugs PPL. So that will help users, it will detect certain size of errors, like if you put a normal prior on a precision of a normal distribution, that should be an error because it's support in one domain. So I'm working on that. And need to decide the type system was sort of domains I would like to structure. That work seems to be going quite well. The bug software's got a nice GUI interface where you can query the model and look at what it's doing. So I need to rebuild those tools for the new internal representation of the model. As I said, I would like to automatically reorder the statements of the PPL so that you can specify the model in the PPL in whatever order you find sort of rational, and then the software will reorder it to have something that it can work on. And mine thing is to get HMC working again. I think it's fairly straightforward to do one at a time differentiation in this new approach. Building the data structures for differentiating all at once is going to be a bit harder. But it's certainly doable because I do that in open bugs. Okay, I think we might be at the end. Let's check.
Cool. Thanks, Andrew, for the excellent talk. Now we have a bit time for some quick questions. I have a question. So you mentioned that the scalability of this new approach might be an issue for very big models. Can you unpack that a bit?
Okay. You need to store a certain amount of information. The idea is that you exploit the conditional independent structure so that you can sample parts of the model on different cores. So you have to distribute the model so that it is in independent bits. Now, when you compile the model, you get the sort of numerical bits built on all the cores. You can just compile the model on all the worker threads. That's fine. As I said, the algorithm to get conditional independent structure, you can parallelize that. So you get that on different cores, but you can't prove easily that they are independent of each other, or have not managed to think how to do that without assembling everything onto one core and then sort of doing a global analysis and then saying, we want this on that core, this on another core, and so on. So that's the idea I'm missing, how to do away with a sort of global overview of the model to get the to be able to split it into bits. I'm sure there's ways of doing it, but you will be sort of shuffling bits from one core to another, saying, those two bits have to be on the same core and moving them around. So that's going to be a bit messy to do. You're basically wanting to move the what I call the array of integers around. If the model isn't too big, you could just have it all on one core and then just say, you know, I only want these bits on this core, this bits on the other core. That might be too wasteful. For the example, there were 400,000 observations, and it was about 50 megabytes, so 10 times 500 megabytes. It's not particularly bad. The actual storage you required to store the data was about 25 megabytes. So if you go really huge models, then you have to think about positioning the data as well. And that's a different problem as well. If the structure of the model is very regular, then it's easy to position the data, but for more irregular structures, it's not at all easy to say, you know, I want this block of data on one core and this on another. So I think there's hope for models up to a certain size where you can do a sort of global analysis on one core. But when you go beyond that, then it's looking harder.
Cool. Thanks a lot, Andrew. We'll have more opportunities for discussions and questions during the short break. In the interest of time, we'll move on to the second talk. Philip, back to you.